Hey guys, welcome to my first video on Taylor series. I'm so excited to help you with this topic because I love it so much. Be sure to subscribe to my channel, and if you're watching from outside of New York, pardon my accent, I'm going to teach you how to do this so easily, and please tune in for the next videos on sine and cosine and natural log. But this one we're going to start with the most basic, which is e to the x. And I'm sure everyone knows how to find the Taylor series for e to the x, but if you watch the whole video from start to end, everything will make sense, okay? And I even show you some graphs. So let's get to it. So I wrote out the steps for you, and we're going to just dive right in. We know that the derivative of e to the x is just itself, e to the x. What we're going to do is we're going to take the function and take the derivative many times. The more times we take it, the better the polynomial function that we are going to create is a better approximation of e to the x. And that's just simply what we're doing. We're trying to find a function that resembles e to the x about a center, okay? So in this case, our center will be 0. So what do? Step 1, take the function and take the derivatives many times. E to the x, e to the x, e to the x, e to the x, e to the x. Took it 4 times. So what do? I substitute the value c for x and I evaluate. Well, what is that c? In this case, I'm going to write a Taylor series centered about x equals 0. So I'm going to put f of 0, f prime of 0, f double prime of 0, and so on. We know that e to the 0 is just 1. So f of 0 is 1, f prime of 0 is 1, f double prime, and so on. Now, these are going to go into this formula down here. So let's switch some colors. This is the formula in order to write a polynomial function or a Taylor series that approximates your transcendental function, which is basically anything that's not a polynomial. So natural log, sine, cosine, and so on. So what I'm going to do in this case is I'm going to say p of x, and I have it on the next page, so I won't do it again. I won't do many of this. I'm going to say this guy here is this guy. So that's 1. Plus this guy here is this guy, x minus, now the c that is basically the number that we're substituting in here, or what we're centered about, which is 0 in this case. So I know that's x minus 0, plus this guy here, that's going to be another one, and I'm going to go x minus 0 squared over 2 factorial. Now under here, I just don't put it there because it's just 1, but it's 1 factorial, 2 factorial, and so on. And I hope everybody remembers what 2 factorial is. It's just 2. Plus, then I take the next one, and I go x minus 0 to the third over 3 factorial. That's just 6, okay? Once we finish this and we clean it up, we get 1 plus 1x plus 1x squared over 2 factorial plus 1x to the third over 3 factorial, and we keep going, okay? So this is the polynomial function for e to the x. So let's take a look. I have this written here, but I want to show you something that's really important. So e to the x is this here. That's what we just found on the previous slide. Okay, what I decided to do is I wanted to show you, because a lot of teachers I don't think show you guys this. This is e to the x, and that's blue. And this is the function that I found. And if you take a look, we have x squared over 2 factorial, that's just x squared over 2, x to the third over 3 factorial, that's just x to the third over 6. And we got this. The blue is our full function e to the x. Our y2, or our red, is our approximation. Now, what you notice here is that this was centered around 0. So this is 0 right here. And what you see is that these two guys pretty much overlap right there. Okay, so right there in green, they're basically touching each other. But a little bit before that, they start drift. You see this here obviously has a horizontal asymptote. This here starts drifting down. This here, they start spreading. So my point is, we use this as an approximation, but it's silly to approximate the value of e to the first or e to the second using this guy here. You should only be using it for like e to the 0 0.1, e to the 0.2. You need to be somewhere in here. Otherwise, the two graphs don't match. Okay, so that's why the center is very important. So this here is our e to the x. And what we can do with this is so many wonderful things. Watch this. Okay, let's write a Taylor series for e to the 2x. Okay, let me get back my red. So we want our function to be e to the 2x. Well, how do we do it? Well, if you go back here, take the function and take the derivatives many, many times, okay? And I did that for you guys. E to the 2x is just e to the 2x times the derivative of the exponent, which is 2. So that's the first guy right here. The derivative of 2e to the 2x is e to the 2x times the derivative of the exponent 2, but times the 2 that's in the front becomes 4 and 8 and 16. What's our next step? Our next step is to substitute the constant c that we're going to be approximating about. So that's 0, 0, 0. But remember, e to the 0 is just 1. E to the 0 is 1 times 2 is 2. E to the 0 is 1 times 4 is 4. E to the 0 is 1 times 8, and so on. Well, we go back and we use our famous equation. So what do we do in this case? Approximation, this would be 1 from him plus 2. And we know that c is 0, so I'm not going to substitute that there, right? Because we're all adults, and we know how to do that. So that's 4. And that's going to be x squared over 2 factorial. And we'll do one more. That's going to be 8, x to the third over 3 factorial. So we can clean this up another time, but basically what you want to do is, it's going to be this. Now you might say, well, is there a faster way, just in case we don't want to keep taking these derivatives? There actually is. So first and foremost, pause the video and understand this, and then we can move on, okay? So now take a look at this, and I found this by taking derivatives many, many times and plugging in the 0, and then using this formula right here. Check this out. If I take our generic e to the x formula, which is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and so on, and everywhere I see an x, I plug in 2x, that will basically give me what I just showed you on the previous page. So we could just substitute, right? Because 2x squared is 4x squared over 2x to the third is 8x to the third over 3 factorial, and so on. So we could just substitute instead of x, 2x, and you could just come up with this here. So that's how we do this. In our next video, we're going to take an example from the AP Calculus BC exam, and we'll apply this. But I hope this makes sense. Remember to subscribe, and I hope that baby Charlie out there screaming in the hallway is not on this video. All right, take care.